All right. Everybody simmer down. It's Friday, huh? Yeah. 3 cheers for Friday. Yeah. Unfortunately, it's also the Friday that is, let's see.
7 days until Tuesday.
Right, yeah, 1 week until assignment 2. So it's this Friday. It's a less optimal Friday than other Friday. So this Friday is missing some properties that are normally associated with Friday. All right, so today we're going to talk. So last time we essentially, 2 times ago we came up with this great idea of, creating these address spaces and as an abstraction, allowing processes to use memory effectively, allowing us to provide them with a bunch of different properties. And last time we pretty much boiled down one of the key core challenges in creating this abstraction to be efficiently translating addresses. So we said we're going to create this level of indirection. We're not going to allow processes to use memory directly. We're going to give them these virtual addresses which had all these nice properties. And today we're going to start talking about how to make the process of translating these addresses efficient, right? Because this is a great idea, but if the performance is so terrible that we can't get it to work, then we would have had to do something else. I mean, clearly this is how things happen, right? But we'll talk a little bit today about different approaches to translating addresses, including one called segmentation, which should finally sort of complete the picture of sort of explaining why you get this segmentation fault, right? When you write badly behaved C code. All right, so yes, assignment 2 is doing, and I think there was a divergence between the syllabus and the due date. The due date is actually Friday at midnight, not Thursday. Sorry, I just ruined another day of next week for you. But anyway, hopefully that extra day will be significant. So next Friday, 11:59 p.m., right? So Friday at midnight, and I will try to remember to update the syllabus later. It's correct on the calendar, right? The calendar has been correct. The syllabus is wrong. If you're having problems with your partner, please contact the course staff as soon as possible. Don't wait. You've waited long enough already if you're at this point. Unfortunately as well, there's only really one thing we can do in these cases, which we're just going to split up your group, right? So if you would rather not be split up, then try to work through things together. If you would like to go your separate ways, please contact us. All right, so any questions about virtual addressing, which was the topic of Wednesday's lecture, all right? So we talked about how we want to introduce this level of indirection, right? And we're going to force processes to translate addresses, right? What were some of the properties of references that we liked compared to giving a process or a task full access to the underlying resource? If I give you a reference instead of direct access, what can I do? What are some of the things I can do? Yeah? Yeah, I can take it away, right? So I can revoke a reference. What else can I do? Yeah, Doug.
You can move it without affecting, you can move where it is without affecting the reference itself.
Right, so I can change what the reference actually refers to, right? As long as I preserve the properties of whatever interface this reference is associated with. I can also create sharing, right, which wouldn't necessarily be that easy to do otherwise. I can move the reference objects, and what's the other thing I can do? Anyone remember? I can actually alter what the reference points to, right? As long as I preserve the interface, right? And virtual memory involves things that you could argue fall into several of, all of these categories, right? Depending on how you think about them. So in order to implement address spaces, what do I need to do? I introduced this level of indirection, so what are we going to talk about today? Yeah, I need to break this direct connection between addresses and physical memory, right? And that's going to require address translation. We talked about things that obey the memory interface as using virtual addresses, right? And the distinction we made was that physical addresses point to memory, whereas virtual addresses point to something that acts like memory, right? That obeys the memory interface. And these virtual addresses gave us a lot more power, right? They allowed us to do these things that we couldn't do with direct physical addresses, right? I can move things around, I can protect things in various ways, and I can move things back and forth between disk and memory, which is important for implementing the address space abstraction, right? All right, so this is like a fill in the blanks, right? So how did we create virtual addresses? There were a couple of different system calls that have the effect of allocating virtual addresses. So Sonny, fill in one of these blanks. Exec, right? So exec is the first place that virtual addresses come from when a process, well, I shouldn't say that because the process was created calling fork, right? But when I change by calling exec, exec lays out a certain set of virtual addresses. What copies the virtual address of the parent process? Fork, right? So that's another place where I get virtual addresses. And these are more accurately the first virtual addresses that the task has access to, right? The same ones that its parent had. What system call extends the process heap? sbreak, and what uses this system call? Malloc, right? And finally, mmap is the system call that creates a virtual address region that actually maps down to a file, right? It's going to look like memory, but the contents are actually going to be stored on disk. That's kind of neat. So we looked at an example of the memory layout that's actually provided by hardware, right? And again, you guys will go through this more in assignment 3, so I won't dwell on it. But the MIPS architecture defines 4 regions of its virtual address space that behave differently, right? The first half get translated by the kernel. That's the process we're going to talk about today. The next 8th of these addresses are actually directly translated by hardware, right, using a very simple mapping. And then the rest of these are, for your purposes, less interesting, right? But the final group up here are kernel virtual addresses that are also can be translated in a variety of flexible ways, but are only accessible to the kernel. So only can be translated when the kernel bit is set when you're running in privileged mode. All right, any questions about this? We've done our brief bit of review. All right, so the goal, and remember, right, we really sort of set out to accomplish a fairly impressive feat, right? I've always sort of speculated that, when whoever came up with this idea was probably like sitting around at a bar somewhere, and they were like, man, it would be so awesome if we could do this, right? Like if we could just translate. And the other guy was like, that's insane, right? How would you ever do that, right? I mean, memory is used all of the time, right? How are we going to translate all these? And of course, we can't have the kernel translate every address. That would be ridiculous, right? I mean, that's a non-starter, right? The kernel is way too slow to do this, okay? And what we want to accomplish, and we're going to talk about several different ways of doing this today, is to allow the kernel to determine how virtual addresses are translated, while allowing the hardware to actually perform as many translations as possible, right? There will be times when the hardware doesn't know what to do and needs the kernel's help. But most of the time, the kernel stays out of the way and allows the hardware to translate addresses according to instructions that it's provided. All right, so the straw man here, and just, and is an example of what we can't do, right? One way of doing this would be to essentially allow processes to ask the kernel where a particular virtual address mapped to, right? So the process would say, I'd like to use this virtual address. Can you tell me what physical address this maps to, right? What's wrong with this? Why can't we do this? I mean, you could do this, right? James?
Well, it can change. The kernel might want to change where that is later, and then it would have to ask again.
Yeah, remember, if I allow processes to get underneath the references that I'm providing, then I don't have all those nice powers anymore, right? I can't, and so remember, processes are never allowed to use physical addresses directly, right? Every address they use has to be translated, right? And it's because if I let them see behind the curtain, right, then, hey, the process just thinks it can use this address in the future, and I might want to move the contents of that memory somewhere else. I might want to allow a different process to use this physical address or whatever, right? So I can't do this, right? So what actually happens is the following, right? So the process says, store this byte of memory at this particular address, right? And then our friendly piece of hardware gets involved, right? The MMU stands for the Memory Management Unit. How many people have heard of the MMU before? OK, good. So this is a piece of hardware. And this piece of hardware's job is to help the kernel translate addresses and essentially to provide the mechanism for translating addresses, right? So the kernel sets the policy by configuring the MMU, and the MMU actually performs the translations according to these instructions. But the first time, I mean, and this is essentially done on demand, right? So the first time a process tries to use a particular virtual address, the MMU doesn't know what to do, right? So what do you think happens at this point? How do I get the kernel involved? Yeah, I generate an exception, right? Remember a couple weeks ago we talked about how software exceptions, right? When we talked about a few of them, one was like divide by 0, right? But I said that most software exceptions are actually completely benign and natural, right? And that's because most of them are generated by attempts by software to use virtual addresses that are valid, but that the hardware doesn't yet know how to translate, right? So essentially, the MMU will say, I don't know what to do. The kernel has to tell me, right? It'll generate an exception. Now we're running in the kernel. The kernel will tell the hardware MMU, this is the translation for this particular address, right? And then well, I guess you would return from the exception handler, and now the MMU knows what to do, right? So now the MMU understands how to process this particular virtual address and how to convert it, in this case, into a physical address. Keep in mind that the process never has any idea where these addresses are being translated to, right? All it knows is that it stored a byte to OX 10,000, and the next time it reads from OX 10,000, it expects to get the same byte back, right? Yeah, of course, gotta say thank you, right? And so essentially here's in diagram form, what we just said, right? I have an address, it goes to the MMU says help, right? I don't know. The kernel says here's how this address is translated, and now the process can complete. Any questions about this? This is a very basic mechanism we're going to keep talking about. Yeah. Yeah, it's like basically just a specialized piece of hardware that you can think of as being on the processor, right? And different. There's a lot of differences in how processors. Well, I shouldn't say there's a lot. There's several. I think maybe we'll talk about this today. I can't remember. There's a couple of different styles of MMU, right? There's actually some memory management units that are even smarter than you might want them to be, and actually try to use kernel data structures to do this translation themselves, right? And then there are MMUs that are called software managed, where they generate more exceptions, but they're constant. And once the kernel tells them what to do, they kind of know, but they don't understand how to find that information themselves, right? I'll talk about this a little bit later, right? But you can think of this as a specialized piece of hardware. Now, could I have one MMU for the entire memory chip? Why wouldn't that be more efficient? It seems like, hey, then I would generate fewer exceptions, right? What would be the problem with that? Yeah, Natasha.
And you'd have to do things more or less in order?
Well, I could still process things in order, but what's the problem with, this translation that I've just told the MMU about, what's important, well, what's sort of an implicit piece of information here that the MMU needs to know? Yeah, Chris.
Well, what process is for? Because each process has the same virtual address.
Right, so this translation is only valid for this particular process. So when, and the kernel, of course, knows what process is running, right? It scheduled this process, and it understands that this is the process that's running on the CPU right now, right? And so this translation isn't even valid on another core, right, necessarily, because that other core could be running another application, another task, another process, and that could happen too. I can't think of a good memory management joke to make about what just happened, so I won't try. So if that particular address, this particular address could be mapped on the MMUs on every core in your system, but it could point to different places, right? And it probably would point to different places, right? Any other questions? These are good questions. Little precursors of things that we're going to get to. All right. Now, the reason, and the nice thing about this, right, is what happens the next time the process uses this particular virtual address? How is the process different? Yeah.
It allocates a different physical memory space.
No, does it allocate different physical memory? I hope not. Yeah.
You want to make an exception.
Yeah, at this point, the MMU knows what to do, right? Remember, kernel is setting the policy, right? It's told the MMU for this particular process, this virtual address maps to this physical address, right? And now the MMU says, OK, thanks. Now I know that. The next time I need to translate this address, I don't need to ask. And that's important, right? Because our whole goal was to not generate an exception every time. Yeah?
So that's the same process?
Yeah. I mean, come on, there's only 2 of these ellipses, like 2 instructions, right? Yeah. No, that should have been more obvious inside. Doug?
But what happens when you pull the memory out from underneath the MMU? Like when you change where it is in physical memory?
You're going to take memory out of the machine while it's running?
Well, no.
That would cause undefined behavior, I'm fairly sure. Although actually, I think there are machines in which you can hotspot memory, I think.
Like
That's
you
wild.
swap something out or
Right, so that's a great question, right? If the kernel does something that causes this address to no longer be valid, what does it need to do? Yeah, it's got to tell the MMU, right? So the kernel and the MMU have to coordinate here, right? And this sort of example is just meant to show you what happens the first time an address gets translated. The first time a new address gets translated, that address will generate an exception because the MMU doesn't know what to do. Hopefully, the next time it gets translated, well, I shouldn't say that. Hopefully, as long as nothing else happens, right? And there's a number of things, as you guys are pointing out, that could have happened. But I'm saying, like, let's say this is a few instructions later, right? Same process running, no context switches. Kernel hasn't moved anything around. This, hopefully, this is our goal, right? Because, to some degree, the performance of this entire system starts to become determined by how many memory accesses can be translated by the MMU without involving the kernel, right? If that number is like, if that ratio is like 1,000 to 1 or 10,000 to 1 or 100,000 to 1, I'm doing good, right? I'm doing well, I should say. I sound like an Olympic athlete or something. If that ratio is like 2 to 1, then I'm not doing so well, right? And so that the performance starts to make a big difference because the overhead of getting into the kernel, I mean, this essentially happens at like 1 cycle, right? This translation, it's extremely fast. The overhead of getting to the kernel is really high, right? So the first address translation is quite slow. Future address translations are really fast. Great question. So any other questions about this before we go on? Yeah? Yeah, OK, so we're going to talk about this, right? Yeah, I'm glossing over a lot of details, which I will ungloss later, right? Yeah. So how does the MMU know this? Like, this is hardware, right? Well, how does, like, this isn't like, it's not me. I don't know whose water bottle this is being attacked. Is that yours? I'm kind of thirsty. I wish I brought mine. Yeah, so, and OK, well, now what happens, right? OX 20,000, what happens? Exception, yeah. And it's possible that these don't complete, right? That's the other thing, so what would this be? What just happened? Segmentation fault, right? And this happens because in this particular case, what the kernel has detected is that this process isn't supposed to use this address, right? There's no valid mapping for it. And at that point, there's really nothing to do, right? There's no way to go on. I just have to kill the process, right? All right. So now let's talk about how, exactly how the MMU stores this information, right? And how this information is communicated and stored to the MMU has impacts both on how the MMU is designed, right? Because this is hardware. This is not like a general purpose processor. These translations have to be done extremely rapidly. And also it has to do, the implications of how I tell the MMU how to translate memory end up having an effect on how I can lay out memory, right? All right, so the simplest potential approach is what's called base and bounds, okay? I assign each process a base physical address, okay? And then a bound, right? The bound is the amount of memory that the process is allowed to use. The way I check to make, and remember, there's a couple of things that the kernel needs to do or that the MMU kind of needs to do internally. Right? So the MMU needs to be able to say, is this address valid? Do I know about it? Do I know how to translate it? And in this case, the nice thing is that the check step is very fast, right? Now, you're probably already starting to wonder, how would I implement my address space abstraction using this? And that's a very, very good question, right? Just bear with me. This is an old system, right? So I check to make sure the virtual address is OK if it's less than the bound. And if it is, the translation requires a single computation, right? I take the physical address, that's configured for this process, and I add in the base, right? Oh, sorry, I take the virtual address and add it to the base, right? All right, so let's walk through an example of how this works. I'm trying to translate virtual address 10,000. What does the MMU need to know about this task in order to translate using base and bounds? 2 pieces of information using base and bounds, right? Not a trick question. What is 1 piece of information? The base. Sonny's like, I can get some easy points. Participation. Yeah. Base and bounds, right? So I need to know the base, right? And I've just made up these numbers, and the bounds, okay? So is this, based on this base and bounds, a valid address for this process to use? Yes or no? I hear maybe, right? How do I tell? I check to see if it's, I use the bounds, right? But how do I check it against the bounds? Is it less than the bounds? Yes. Yes. So this is a valid address. Now how do I translate the address? I add it to the base, right? So, and conceptually what you can think of is that I've essentially given this process permission to use a contiguous chunk of physical memory, right? The chunk starts at the base and has a size of bounds, right? And so here, that address that I've tried to translate is less than my bounds, and this translation can complete, right? And I've translated it by simply adding it to the base. I don't do this on the examples in class, but I will tell you, because I know that you guys are probably angry with me right now as you're trying to do assignment 2. So I'm trying to earn some brownie points back from the class. When I ask you guys to do these on exams, we always use base 10, right? Because no one likes to add hex, in a 1-hour exam. At least not me. I don't know. Maybe you guys are getting soft. How many people can add hex very quickly? Okay, well, sorry, you're not getting the only A anymore. Yeah, exactly. I used to get exams when I helped teach this at Harvard, where people would have little tables in the back where it was like A plus C equals whatever. It's just terrible. So anyway, we don't do that. We use base 10, right? Because people know how to, if you don't know how to add base 10, there are problems that you have that I can't help you with. So we've mapped this into the correct address. Does everyone understand how this works? This is pretty simple. Yeah, Danny. No, stop getting ahead of yourself. Yes, there was a big problem with this approach, right? But let's just go through one more example. Okay, is this address valid?
Yes.
Where does it map to? See, you guys aren't as good at adding hex as you thought you were. Yeah, there you go. 64E80. What's that?
That's what computers are for.
Yeah, exactly. Computers are good with hex. What about this address? Is this address valid? No. Boom. Yeah. So this address would result in a segmentation fault. Okay. But as Damien's pointed out, what's wrong with this? Right? Is this a good fit? I think this is on the next slide actually. Is this so? The nice thing about this, let's just give this some credit. This is very simple, right? The MMU only needs 2 pieces of state, right? And then it can translate a potentially large number of addresses. So when you guys think about MMU designs, you want to think, first of all, what does the MMU need to know, right? This is hardware, so it can't know like an infinite amount of stuff, right? And then the second thing is, what's the computation it actually has to do in order to translate addresses, right? And this is great. 2 pieces of data, right? And 1 addition. So that's awesome, right? Actually, sorry, so there's 1 comparison I have to do, because I have to check the address against the bounds. But then the translation is 1 addition. That's pretty cool. But as David pointed out, is this a good fit for our address space abstraction? What's wrong with this? Remember, address spaces were giving every process this huge chunk of memory. Yeah, Sumit. Well, I mean, can I even support the address space abstraction using this? No, because I can't, first of all, I can't give anybody more memory. I can't make it look like they have more memory that they can map than the physical machine has, because even if I put their base at 0, the bound is still limited to the amount of physical memory I have, right? And remember that address spaces also encouraged processes to spread out, right? So I've got a little bit of stuff like way at the bottom of my address space and a little bit of stuff way at the top of my address space, and there's like gigabytes of unallocated virtual address space in between those, right? And this system cannot support that, right? And well, I just gave the answer away, right? So, you know, if I tried to do this, even okay, so let's say that I said, okay, I like base and bounds. Let's change the address space abstraction. Instead of a 4 gigabyte address space, I'll give you a 1 megabyte address space, right? And then, you know, I've got 256 megabytes of RAM, and I can run 256 processes, right? But you know, there's either one of two things that are going to happen. Either the processes still aren't going to use much memory, and there's going to be a lot of unallocated memory inside every one of these allocations, right? In which case, I'm going to have internal fragmentation. Or they're going to need more memory than I can provide them, and that's a separate problem, right? And you know, again, there's like these big gaps of unallocated space inside most process address spaces, right? And this is a nice thing about the address space abstraction, but it makes it a bad fit for base and bounds, right? All this unallocated red area with big arrows pointed at it. Okay, so, but base and bounds is kind of nice, though, right? The simplicity of it is very attractive. But can I sort of extend it just slightly and get this to be a better fit for my address space abstraction? What would be one way to sort of do a minor modification to this approach that would allow me to actually cover address spaces more efficiently? Yeah, Mac.
What if you had like a base and bounds for each one of those segments within the process?
Yeah, what about if we can do multiple bases and boundsies, right, per process, right? And this is what segmentation is, right? So this is the next approach we're going to talk about. This is actually, this approach, despite the fact that it's different in certain ways than what real systems actually do, has properties that have survived to present systems, right? And this is because segments are actually a really nice way to organize information about the address space, because processes tend to organize their address space in these little contiguous chunks, right? I have an area where my code is. I've got the stack that's used by one thread, or the stacks that are used by multiple threads. I've got a heap where I do my dynamic allocations. And the way to extend this is I use one segment per code region, right? Each one of them can grow and can be a separate size sort of independently. And I can protect each one of them differently, which is nice, right? So that's a nice additional feature that I wasn't going to be able to get with just one base and bounds, right? I would basically have to mark the whole, you know, process address space as read, write, and execute. Otherwise, nothing would work, right? So how do I do segmentation, right? So each segment now needs one more additional piece of information, right? Which is I need to know what the start virtual address of this segment is. But other than that, it's base and bounds, right? The start virtual address tells me where that base and bounds is within the process's virtual address space. And the base physical address and bound work the same way, right? So to check whether or not a virtual address is valid, I need to do a little bit more work. I need to look at if the virtual address is inside some segment, right? Does there exist a segment such that that virtual address that I'm trying to translate, this is also how I figure out which part, like which memory region to use, right? I need to figure out, is this virtual address inside some segment that the process has been configured to be able to use? So I essentially look through all my segments in the segment table, which the MMU has to maintain. And I look to see if the virtual address falls between the start of a segment and the top virtual address of the segment, which is basically the base of the segment plus whatever the bound of that particular segment is, right? And now to translate it, it's once I've figured out which segment to use, right? The translation is also fairly straightforward. I lop off the beginning of the segment, and then I add that offset to the base physical address, okay? Happily, I have an example, right? That gets a little bit more complicated, right? So, okay, what happens? OX 10,000, what's the first thing I have to do? Exception, right? MMU doesn't know what to do, and now what does the kernel need to tell it? 3 pieces of information. So I need to know where the segment starts. I need to know the base physical address, right? And the bounds, right? So this is a virtual address, this is a physical address, and this is a length, essentially, right? Now, what would happen if this address was actually going to generate a segmentation fault? What would the kernel do at this point? Or what would the kernel have not been able to locate? This information, right? If there's no segment that the process has been configured to use, the kernel will detect that and kill the process, right? So that is a segmentation fault, and that's why it's called what it is. All right, so now how do I translate this? Now I've located a segment. Where is this address going to map? Well, first of all, is the address valid? A segment exists that at least looks like, and how do I know it's valid? It's greater than blank and less than blank. It's greater than OX 10,000 and it's less than OX 11,000, which is the start plus the bounds, right? So it's inside this segment. Good. Now I can translate it. Where does it translate to? It translates. So okay, so this marks off a segment which maps to some area of physical memory. And this address translates to the very, very first address of the segment, right? I take the virtual address, I lop off the start, that gives me 0, and I add it to the base. Pretty straightforward. Paul?
You don't know if the segment is at the beginning of the process's address space, so you have to be careful of null pointer at the beginning of it?
So how would I use this? So let's say I wanted to handle sort of null pointer exceptions. How would I use this scheme to do that? So this is not a null pointer, right? Or it could be, but it's a really big null pointer exception, right? Like I allocated some huge structure, and that can happen, right? But how would where would I not allocate a segment if I wanted to help processes debug null pointer exceptions? I wouldn't allocate a segment that started at 0, right? This segment is probably far enough from 0 that either I'm still going to be able to catch most null pointer exceptions. So maybe this is the first segment in the process's address space, right? And so I've reserved essentially sort of 10,000 hex for catching null pointer exceptions. And if you create null pointers that are bigger than that, then you're on your own, right? I can't catch every null pointer exception. Some of them, you know, some of them are going to sneak through if you've broken things badly enough. Yeah, assume.
Does that start has to be greater than the virtual address, or can we can start from that start?
In this case, it's inclusive, right? So I'm going to lop off the start. So as long as the address is greater than or equal to the start, I'm fine, right? This gives me the ability to address physical address 43,000. Good questions. Any other questions? Let's do another example, right? What about this address? What happens here? What does the MMU do? Well, what would it do before generating an exception? It tries to find it, and it's in the tables that have been configured, right? And it says, OK, well, it's not inside this segment. So what do I do now? Ask the kernel for help, right? And what can the kernel do at this point? It could kill the process, or it could tell the MMU what to do, right? And in this case, I think I've decided for some reason, and now I am not helping the process catch null pointers, right? I've disabled its ability to do this at least somewhat. But this is just because I didn't want the addresses to get too big, right? OK, so the kernel says, OK, actually, there's another segment down at the beginning of the address space. It starts at virtual address 100, and it has size 500. And the physical address where the segment is currently 16,000. Yeah?
Isn't that a different process?
No, it's the same process. Yeah. Why would that be a different process? Yeah. Yeah, just in these examples, you can assume the process is the same unless I tell you that something weird happened. Yeah.
Does kernel give a new segment every time it is not able to find that one in MMU?
So anytime the MMU generates an exception, will the kernel return with a new segment? No. I mean, if the process tries to access an address that it hasn't been configured to use, then the kernel will kill it, right? So the assumption here is that something already gave the process, that's a good question, the permission to use these virtual addresses. They may have been configured by exec. They may have been left over from a fork call. You know, they might be in my stack region. These don't look like stack addresses, but just pretend, right? Or maybe I used mmap to create them, right? But the idea is before I started running, something that I did previously has given this process the ability to use these virtual addresses. Yeah, it's a good question. There's a question over here. Yeah.
Are the physical addresses in a segment contiguous?
Yes, right. So we'll get to that. Let me come back to that in a minute after I go through this example, because that's an implication of segmentation that's important to deal with. Yeah.
So the same thing that you were talking about before, is that also what determines the size of the segment too?
Yeah, exactly, right? So for example, maybe this is the process's code segment, and it just happens to be 1,000 wide, right? Yeah. So these have to be set up, and in general processes, the compiler and the process will try to reserve as little virtual memory as possible. Right? No point taking stuff you don't need.
So where is the segmentation info stored?
Yeah. Okay. Good question. Right. So the other thing I'm not showing is somewhere up here. Right, and we will talk about how this has to happen too, right? The kernel has to be able to locate this information, right? So the kernel needs a data structure in order to do this.
Who maintains the segmentation?
Who maintains the segmentation information? The kernel. Yeah. So remember we talked about the ways that processes can actually configure various parts of their address space to be valid. All those ways have to adjust some information the kernel has to maintain about where these addresses mapped, right? And kernels have some very nice data structures for doing this. However, keep in mind, most of the performance of these schemes is dictated by the MMU, right? Because by the time I get to the kernel and I have to look up some information, I'm so slow anyway, it almost doesn't matter, right? Kernels still try to have efficient data structures for mapping these addresses to whatever information they need to find for the MMU. But again, the efficiency of those data structures doesn't dominate the performance of your virtual memory subsystem. That's dominated by the hardware translation and how effective that is. Good questions. Any other question? Yeah, Mac.
You mentioned that processes like this, it's spread out. So
Uh-huh.
what was the boundary limit spreading it? Is it effective?
No, I mean, if I have a small segment, well, this is my physical memory, right? But if you imagine my address space, if I have a small segment here and a small segment here, the nice thing about the segmentation approach is I can cover each one of them with a small segment, right?
Taking like huge chunks of memory, they're just kind of spreading out.
No, when I meant spread out, I mean they like to put things far apart.
Okay.
Yeah, okay, yeah. I guess that's a little confusing, right? So when I say processes like to spread out in their address space, I mean that the stack is at one end and the code is at the other, right? There's a lot of unallocated space in between those two things, but they're far apart in virtual memory, and that's what killed the base and bounds approach. Right? All right, so I have another segment that maps to virtual memory here, and I can map this. Does everyone understand how this gets mapped? Is that actually correct? Yeah, it is. Right. So how did I do this, right? I just confused myself. I took 400. I subtracted 100. That gave me an offset of 300 into the segment. I added that to my base, and I'm up here, right? All right. And then, OK, so here's an address. What happens? You don't know what happens yet. So what? It says dead beef. It could be good. It could be a good address. It's like, yeah, I think this is a fraud hint. Anyway, it's just a little hint. But dead beef could be a valid address. It just happens to not be in this particular case. Right. All right.
Couldn't it revert in OS or sys 161 for some reason?
No. I can answer this question offline later. But OK, so is this the ideal solution? Right? There are some nice properties about this. It's a good fit for the address space abstraction. It allows me to cover the entire address space with segments that are both, they're a nice fit for how the process is actually using memory, right? I have a code segment, right, where all my code is located. I can mark that segment as read-only. We didn't talk about permissions here, but I can do that potentially at the MMU level. I can tell the MMU, generate an exception if the process tries to write into this particular segment, if it issues a store as opposed to a load. I can also mark segments that cannot be executed from, right? So if I don't want the process to execute code from a particular segment, I can tell the MMU, do not load and do not fetch and decode an instruction from this range of addresses, right? So this is nice. The nice thing about this is it's still pretty simple, right? This starts to become a little bit gross, right? As the number of segments grows, potentially, depending on how this is done in hardware, I end up having to do more sort of hardware comparisons. There's some persistent whispering going on over here. Can you guys? Thanks. So as the number of segments grows, the amount of time it takes me to locate the segment is going to potentially grow. I could probably play some games in hardware to make this log n or something like that, but or even constant time, which we'll talk about next time. Sorry. And The translation is also quite simple once I've located the particular segment that I want to use, right? Just one addition. And again, the nice thing is that I can organize and protect these regions of memory appropriately. And it's a nice fit for address spaces. Allows me to cover the address space with less waste of virtual memory and less internal fragmentation, right? But as someone has pointed out, a significant con here is that it still requires the entire segment to be resident in memory, right? Does this make sense? If I need to map an address in a segment, that whole segment has to be in memory. It also has to be contiguous in memory. So what are two implications of this, right? So there's a potential for external fragmentation, right? Imagine my memory space is sort of split up into these little chunks, and a process tries to access an address inside a segment that's too large to fit into either any of the little holes that I have for it, but I have enough available memory, right? So I have an external fragmentation problem that segments create, right? I can have enough memory between my allocations to satisfy the request to bring a segment in and use it, but I can't actually bring it in without moving a bunch of stuff around. Now, can I move segments around in memory?
Yes.
Yeah, that's one of the nice things about virtual memory, right? But what do I have to do that? I gotta copy stuff all over the place, right? I gotta take your 1 gigabyte segment and like move it to the left by 1 byte, right? I mean, that's going to take a long time, actually. And so it'll be a really unsatisfying operation when I'm finished, right? Just so I could put this one segment right into that slot that's left, right? So that's not good. There's also an internal fragmentation problem with segments, right? Can anyone spot what that would be? Where's the potential for internal fragmentation? I mean, technically, yeah.
You have a bound section again, and that's the fixed block. You don't necessarily need that whole block, the whole segment block.
I might not be using all of the memory inside a segment, right? And I can't get rid of little pieces of it, right? Once I brought the segment in and I've allowed the process to use it, there's no way to take away a part of it, right? So for example, if one of these segments is the process heap, and the process has been allocating all these dynamic objects and it's not using a lot of them, there's no way to sort of go in there and get them back, right? So again, segments are good. We got closer to what we wanted. But what's the real ideal here, right? We never actually talked about what we really wanted, right? Sometimes, in life it's good to step back and be like, am I happy, right? Like, what would I really, really like, right? And ideally what I would like is fast mapping from any virtual byte to any physical byte. This is what I would like the MMU to do, right? I can tell it essentially in an incredibly fine-grained way how to map any virtual byte to any physical byte, and it'll just do it, right? None of this segment stuff, none of this base and bounds, none of this sort of stuff, right? And we already talked about how the operating system cannot do this itself, right? And we're using hardware already. We're using the MMU, but is there a way to accomplish something a little bit more like this, right? Where I could essentially have the MMU set up to do completely flexible mapping of any byte. Forget offsets, forget base and bounds. One of the things that systems do when something gets slow, right? This is another sort of common system design principle, is we put a cache in front of it, right? So when disks are slow, right? But hard drives have memory caches on them for this reason, right? Your memory is slow, right? What's the cache we put in front of memory? Yeah, it's like an L1, L2, L3 cache. I mean, your system is full of caches, right? I mean, actually, you can think of computer systems as just an array of caches, right? Everything on top caches everything on the bottom as you go up. Everything on bottom gets progressively slower, way slower, but also bigger, right? So at some level, registers are caching your disk, right? But you only have 32 registers, and you have 32 terabytes of disk, right? So big difference in speed, big difference in size. So one of the hardware techniques we're going to talk about to make this process fast is what's called a translation look-aside buffer, or TLB. A lot of people have heard about TLBs from their hardware classes, right? How many people have done this? OK, good, right? So TLBs use this sort of fun idea of what's called content addressable memory, right? Meaning memory that I can actually address by its contents rather than by location, right? So I can tell the TLB, look up this particular address. That's what I want, right? I want to be able to ask the TLB or ask the MMU, which physical byte does this virtual byte point to, and have it do this extremely fast. I think I'm going to stop. Maybe I'll get through the TLB example, and then we'll talk about PageIt next time, right? Actually, you know what? Maybe I won't. I think I'm going to stop here. On Monday, we will talk more about TLBs. We'll go through some examples, and then we will get to paging, which is the least bad solution to the problem of translating virtual addresses to physical addresses.